Yes, welcome back again. We will start the oxidation state. I will discuss detailed. I will discuss in detail oxidation state because in your new textbook, this oxidation state is discussed in very short. The students who are appearing for the competitive exams for the NEET, JEE, and CET, one question is there 100% for the oxidation state of transition series elements or on this D and A block elements. So we have to remember this entire table. From scandium to manganese, we can see here the oxidation states are increasing. Scandium, there is a 1 unpaired electron, titanium 2 unpaired electron, vanadium 3 unpaired electrons, chromium 5 unpaired electrons, then manganese also 5 unpaired electrons. From this iron, from this Fe, the number of unpaired electrons are decreasing, so the oxidation states are also decreasing. So if the number of unpaired electron increases from scandium to manganese, see the oxidation states are also increasing, and this manganese shows the highest oxidation state in the transition elements. It shows +2, +3, +4, +5, +6, and +7 oxidation state. We will discuss this oxidation state one by one. First, we will discuss the oxidation state of scandium, titanium, and vanadium. The scandium having the atomic number is 21, 4s2, 3d1. Then titanium is 4s2, 3d2, and vanadium is 4s2, 3d3. Because these are the continuous elements, scandium, titanium, vanadium, like this is a 3D series. So the outermost electronic configuration of scandium is 3d1, 4s2. It can show the oxidation state +2 also and +3. But scandium +2 oxidation state is very, very less stable. That's why it is not written. +3 oxidation state is more stable. When +3 oxidation state means 3 electrons will be donated. So 3 electrons will be from 4s 2 electrons, and from 3d 1 electron will be given. So 3d will contain the 0 electrons. See, when 3d having the 0 electrons, so it will be the stable oxidation state. In case of titanium, see the electronic configuration of titanium is 3d2, 4s2. So when the 4 electrons are given, so +4 oxidation state is the stable oxidation state of the titanium. Then I am coming to the vanadium. The outermost electronic configuration of vanadium, we can see 3d3, 4s2. 3d3, 3 electrons are there in d orbital and 2 electrons are there in s orbital. So if these 3 and these 2 electrons are donated or given, it shows +5 oxidation state. In +5 oxidation state, this 3d will contain 0 electron. In case of +4, this 3d having 1 electron. In case of +3, this 3d having the 2 electrons. In +2, this 3d having the 3 electrons. So it shows +2, +3, +4, +5 oxidation state. But in case of +5 oxidation state, the d orbital do not contain any electrons. So +5 oxidation state is the most stable oxidation state of vanadium. The d block element shows variable oxidation state because they contain the unpaired electrons. As the unpaired electrons are more, the oxidation states are also increases. Then I'm coming to the oxidation state of this chromium. You know, this chromium shows exceptional behavior. The outermost electronic configuration is 3d5, 4s1. So if this 1 electron is given, means chromium actually it should show +1 oxidation state should be more stable, because if this 1 electron is given from this 4s, 3d contain 5 electrons and it is half filled. Generally, when the metals contain exactly half filled electrons, it is more stable. But this chromium is exceptional. Only one compound is there actually in +1 oxidation state with pyridium. So this chromium shows only one compound in +1 oxidation state, that is with pyridine. That is one complex is there in which the chromium having the +1 oxidation state. So generally this chromium shows oxidation state In case of +2 oxidation state, these are the examples. It is called as chromous chloride. Chromous chloride, the formula is CrCrCl2 and chromous sulfate CrSO4. In these two compounds, chromous chloride and chromous sulfate, the chromium having the +2 oxidation state. +2 oxidation state means the d orbital having the 4 electrons. In case of +3 oxidation state, the d orbital having the 3 electrons. In +4, 2 electrons. +5, 1 electron. And +6, 3d0. So +6 oxidation state is most stable oxidation state of this chromium, because all the electrons from this d and s are also given. +3 oxidation state shows only one compound, that is chromium chloride, CrCl3. +2, it is chromous, +3 chromium. Then +4 and +5 oxidation state are unstable. So chromium do not shows any compound in +4 and +5 oxidation state. And this +6 oxidation state is very stable, because in case of +6 oxidation state, all the electrons from 4s and 3d are donated. So +6 oxidation is very stable. The name of the salt is chromate. Chromate, it is K2CrO4. In this chromate, the oxidation state of this chromium is +6. In case of dichromate, this is a potassium dichromate, K2Cr2O7. The oxidation state of chromium is +6. In case of this chromyl chloride, I want to remind you, this chromyl chloride, it is used in Itard reaction. Remember, this chromyl chloride, this complex is formed. Those students who are preparing or revising the organic chemistry, this chromyl chloride, it is used in the Itard reaction. Then, so +6 oxidation state is more stable. Chromium is a good oxidizing agent in +6 oxidation state. You know, this K2Cr27, it is a very strong oxidizing agent. In your textbook, these oxidation states are not given. Oxidation state of manganese. So for the board examination, the question is asked on this manganese always. For example, I will give the question for 3 marks. Write the different oxidation state of manganese. It is having 1 mark. And why +2 oxidation state is more stable. This question is asked for 2013 for 3 marks. So for 1 mark, it is expected from the students to write all the oxidation state of manganese, that is +2, +3, +4, +5, +6, and +7. So these oxidation states are shown by the manganese. And the next question is, why this +2 oxidation state is more stable? Because if manganese shows +2 oxidation state, means this 3d orbital is having the 5 electrons. So the general electronic configuration is considered in case of manganese, C, 4s2, 3d5. So these 5 unpaired electrons are there. If these 2 electrons are given, the d orbital contains 5 electrons. So it becomes half filled, because the capacity of d orbital is 10 electrons. Exactly half filled, it is a stable electronic configuration or stable oxidation state. So in case of manganese, +2 oxidation state is more stable, as it exactly becomes half filled. So +2 oxidation, in case of +2 oxidation state, these are the salts are given, MnCl2. It is called as manganese or manganese salt, MnCl2, in which manganese having the +2 oxidation state. +3 and +5 oxidation states are very unstable. The manganese do not show any compound in +3 and +5 oxidation state. Then I am coming to the +4 oxidation state. This MnO2, manganese dioxide, in which this manganese is having the +4 oxidation state, because you know oxygen is having -2, 2 into -2, it is -4. So manganese shows +4 oxidation state. Then in case of manganate, manganese shows +6 oxidation state. It is K2MnO4. Remember, this is potassium manganate, and KMnO4, it is a potassium permanganate. In case of manganate, the manganese having oxidation state is +6. And in case of permanganate, this manganese having the oxidation state +7. So these are the various oxidation states shown by the manganese. Remember, the question is also as for the board examination. Because manganese is the only element in the 3D series which is having the maximum oxidation state from +2 to +7. So +7 oxidation state is a very good oxidizing agent. That's why KMnO4 acts as a oxidizing agent. Then I'm coming to the oxidation states of iron, cobalt, and nickel. Generally, this iron shows +3 oxidation state and +2 oxidation state. So I am first coming to the iron. So this is outermost electronic configuration of iron: 4s2, 3d6, cobalt is 3d7, nickel is 3d8, and zinc, copper is 3d10, and zinc is 3d10 also. But in case of copper and nickel, the 4s is in case of copper, atomic number 29. It shows exceptional behavior. 4s1 3d10, and in case of zinc, it is having 4s2 3d10. This is the difference in copper and nickel. In the next slide, we will discuss the oxidation state of copper and zinc. But see the outermost electronic configuration here, number of unpaired electrons will be decreasing from this iron, cobalt, nickel, because pairing will started. So iron generally shows +2 and +3 oxidation state. +3 oxidation state, it is a ferric compounds. Ferric chloride is one good example. And +2 oxidation state, these are called as ferrous compounds. Ferrous +2 and ferric +3, remember. Ferrous chloride, ferric chloride. This +4 and +5 oxidation state of ions are very, very less stable. There is no any compound. It is found in +4 and +6 oxidation state. But in case of +6 oxidation state, iron is called as ferrets. So for the 1 mark or 2 mark question, they can ask the question for board exam, write the name of the compound in which the iron is having +6 oxidation state. So remember the name, it is potassium ferret, K2FeO4. This compound shows in which the Fe having the +6 oxidation state. So generally +3 and +2 oxidation states are more common oxidation state, but only in case of ferrets, +6 oxidation state, it is obtained by the iron. Ferrets, remember this ferrets, ferrets +6, ferric +3, ferrous +2. Then this cobalt and nickel shows +2 and +3 oxidation states. +2 oxidation states are more stable. In case of generally, cobalt shows +3 oxidation state, but nickel shows +2 oxidation states. Then the oxidation states of copper and zinc. This is a exceptional behavior of copper because 1 electron it is shifted to the d electron to acquire the extra stability. So copper having the 10 electrons. Zinc is already having the 10 electrons. It is not considered as a transition element, but zinc, this always shows +2 oxidation state because when these 2 electrons are given, it becomes stable. It is completely filled. So zinc shows only +2 oxidation states, but copper can show +1 oxidation state and +2 oxidation state. In case of +1 oxidation state, it is called as cuprous salts. In case of cuprous salts, copper having +1 oxidation state, and in case of cupric salt, copper having the +2 oxidation state. See, this is a good example, copper sulfate or cupric sulfate, in which copper having +2 oxidation state. And in case of cuprous chloride and in case of cuprous iodide, this copper having the +1 oxidation state. So remember these oxidation state, one question is there for the competitive exam also and for the board exam also. Then I'm coming to the physical properties of the first transition series, that is a 3D series from scandium to zinc. So I am considering only scandium to zinc. I'm not considering the other elements. So these are the physical properties of transition elements of the first series. They shows the metallic property generally because All these are called as transition metals. They are very hard. They are having the high tensile strength. They having the properties of all metals. Metals are hard. They having high tensile strength, lustrous, malleable, ductility, and they also form the alloys with other metals. Then they are also the good conductor of heat and electricity. So all these properties are properties of metals. I am not discussing in details, but I want to focus one thing. This zinc, cadmium, Hg, and this manganese, they do not having the metallic structure. Remember this zinc 3d10, cadmium is also 3d10, mercury is also 3d10, manganese 3d5. So this is they have the metal other elements metals having the metallic structure, but except this zinc, cadmium, magnesium, and mercury, they do not have the metallic structure because of the electronic configuration. They are generally very hard, having the low volatility, except zinc, cadmium, and Hg. These are very soft. Zinc is very soft, cadmium is soft, mercury, exists as a liquid state at room temperature. So these are exceptional. Zinc, cadmium, Hg, these are exceptional because their d orbital is completely filled. D orbital is completely filled. They having the high melting and boiling point. Also, there is exception of zinc, cadmium, and Hg, because no unpaired electron is there. In case of zinc, cadmium, and Hg, there is no unpaired electron. If there is no unpaired electron, they do not form the covalent bonds. If they do not form the covalent bonds, they will not become hard. So all the next properties depend upon the number of unpaired electrons. If the number of unpaired electrons are more, then they will form the more covalent bond. If the covalent bonds are more, then the metal will be very hard. If the metal will be very hard, the melting and boiling point will be high. So all the properties depends upon the number of unpaired electrons. Yes, hardness of the metals. This hardness of the metals depend upon the presence of covalent bond. And the covalent bonds are due to the presence of unpaired electrons. If the unpaired electrons are more, the covalent bonds will be more. And if the covalent bonds will be more, the greater will be the hardness of the metal. So the metals such as chromium, molybdenum, tungsten, these are having the maximum number of unpaired electrons. That's why this chromium, molybdenum, and tungsten, these are very hard. Remember, I will show the graph, melting point graph. This is zinc, cadmium, and Hg. These are very soft because they do not having the unpaired electron. So we can see the chromium, molybdenum, and tungsten. See this graph. This is a graph of melting point. This is tungsten, which is in third series. This is 3D series. This is a 4D series, and this is 5D series. If we see the graph, this chromium in case of 3D series, which is having the highest boiling point, then this molybdenum, which is having the highest melting and boiling point, and this tungsten having the highest melting and boiling point. This is because the number of unpaired electrons are more. If the number of unpaired electrons are more, then they will form the more covalent bonds, and if the covalent bonds are more, the hardness will be more, and the melting and boiling points will be more. So if we see the trends of this melting point, I will explain. I am interested in this only, this series. I am interested only in this 3D series from scandium to zinc. So initially the melting and boiling point increases up to the chromium. Chromium attains having the maximum melting and boiling point because the number of unpaired electrons are increases. From this chromium to this, suddenly in case of manganese, the melting points becomes down, and again it will be increases, and it is stable to zinc. So why this is happening? This is because of the number of unpaired electrons. See, the number of unpaired electrons are increases up to the chromium, so the melting and boiling point will be more. Now I am explaining this manganese, then this technetium, Tc. This is having the very less melting and boiling point because these two metals having the complex lattice structure. So the melting and boiling points also depend upon the lattice structure because the close packing. The answers are given here. I have given the detailed explanation why the manganese and technetium having the lower point, lower melting and boiling point, because the last line is written here. The manganese and remember the name, it is a technetium, TC. Unexpectedly, they are having the lower melting point because of their complicated lattice structure. So, generally from this D5 electronic configuration up to D1, D2, D3, D4, D5, unpaired electrons are increasing. If the unpaired electrons are increasing, then the number of covalent bonds are also increasing. So the hardness increasing and the melting and boiling point will be increasing. So for the board examination, they will ask for the 1 mark question or 2 marks question. Write the trends in melting and boiling point. So what is expected from the student? This graph is not expected. The values are also not expected. Only it is expected. Why? The melting and boiling point increases up to D5. So up to D5, number of unpaired electrons are increases. Again, from this iron to zinc, number of unpaired electrons are decreases. So the melting and boiling point decreases, remember. So I am coming to the next trend, atomic and ionic radii. You know what is mean by atomic radii and ionic radii in 11th standard. We already discussed the periodic trends of S block elements also, in P block elements also, and in periodic table chapter we already discussed what is mean by atomic radii. It is nothing but the distance from the nucleus to the outermost shell. This distance is called as atomic and ionic radii. As the outermost electron go away from the nucleus, so the atomic size will be increases, and as the outermost electron come closer to the nucleus, atomic size is decreases. Now, in case of scandium to zinc, we will discuss the periodic trends in case of 3D series only. So I have this graph. With the help of this graph, I will explain. This is a scandium, titanium, then this is vanadium, this is chromium, this is manganese, iron, cobalt, nickel, copper, and zinc. So this is a 3D transition series, this is a 4D transition series, and this is a 5D transition series. So if we observe this graph and these values are also given, see the atomic number is increases from left to right, scandium to zinc. So, but we can see here, see the atomic radii is decreases. It is 164 for scandium. With the graph also we can see here, scandium is having the atomic radii is very high. Then as we come to this chromium, we see these values. With this value, I can explain 164, then 147, then 135, 129. So up to this chromium, we can see it is suddenly decreases. Why this is this decrease is there? Because from this scandium to chromium, the electrons are added in the same shell. So initially the atomic size decreases up to this chromium, then it becomes constant up to this copper, and in case of zinc it is increases. So this is expected from the students. So it is written in bold type also. Values are not expected from the students, only the trends are expected. So if the question is asked for the board examination, what we have to write? The atomic and ionic size decreases from scandium to chromium, then it attains a constant value up to copper, and at last it is increases. Now why this is happening, I will explain. So from this initially what is happening, as the number of electrons, unpaired electrons are more here up to the manganese, means electron up to the chromium. See, up to the chromium what is happening, the electrons are added in the same shell. Actually, from this scandium to zinc, electron is added in the same shell to the 3D series, but the pairing starts from this ion, remember. Pairing starts from this ion Fe26, pairing will be started. Up to this manganese, there are only 5 electrons. Up to this manganese, there are only 5 electrons in this iron, cobalt, nickel, copper, and zinc. From this Fe onwards, Fe to zinc, pairing will be started. So initially what will happen, the nuclear charge increases. So initially the nuclear charge increases. At the nuclear charge is increases, you know, it will push the electron towards itself, and the atomic size will be decreased. Atomic size will be decreased up to the this 127, up to the manganese. Means up to the scandium, from scandium to manganese, atomic size decreases. Then almost it becomes constant. See, it is 26, 25, 25, 28. This is a constant because there are two effects. One is a nuclear charge effect and another one is a shielding effect or screening effect. So from this iron to iron, cobalt, nickel, and copper, the nuclear charge effect and the screening effect is balanced here. Nuclear charge effect and screening effect is balanced up to this copper. And in case of zinc, what will happen? In case of zinc, all the electrons are paired there. There is no any unpaired electrons. So due to this pairing, what will happen? Due to this pairing, this repulsion of the electrons will be more in case of zinc. I am discussing why this zinc is having the higher atomic size, because in case of zinc, as there is no any unpaired electrons, all the electrons are in pairing. So due to this pairing, what will happen? The attractive force is less. Means the effect of nuclear charge will be less and the effect of the shielding effect will be more, because due to the pairing, what will happen? They will repel the electron. They will repel the electron, so the atomic size will be increased in case of zinc, remember. So this is exceptional in case of zinc because the repulsion will be more. So it is explained here. In case of zinc, what is happening? The repulsive interaction between the added electrons in each orbital is more than the attractive force. So this is the reason why the zinc is having the more atomic size. Initially, what is happening? Nuclear charge is increases. Then in the middle, the nuclear charge and shielding effects are balanced. And at the end, due to this pairing, repulsion is more. Repulsive interaction is more than the attraction. So the zinc is having the oxidation, sorry, atomic size increases in case of zinc because of pairing is there. So generally this question is asked for the board examination in case of transition series. Why the zinc having the higher atomic size than this manganese or iron? These questions are asked for the examination. So if you understand the theory, then you can write the answers. Don't write these values because values are not expected, but the trends are expected only. Why zinc is having more atomic size than this nickel, cobalt? Because from this manganese to copper, the shielding effect and nuclear charge effect, these are balanced. And in case of zinc, the repulsive interaction is more than the attractive force. So this is expected from the student. Now I'm coming to the ionization energy. Ionization energy in 11th standard, we already discussed the definition of ionization energy. It is nothing but the amount of energy required to remove most loosely bound electron from the isolated gaseous state. So again, the definition is given for your understanding purpose here. Ionization enthalpies of these transition metals are intermediate between S block elements and P block elements. As you know, these transition elements are kept in between S block and P block. All the properties are also in between S block and P block. You know, S block elements are more electropositive, P block elements are more electronegative. So the properties of this transition elements are also in between electropositive and electronegative. Ionization in enthalpy values are also in between S block and P block. So the properties are also in between S block and P block. As you know here, as we discuss here, atomic size decreases, then attain the constant value, and at last it is increases. As the atomic size decreases, ionization energy will be increased, because these are exactly opposite to each other. Atomic size and ionization enthalpies are exactly opposite. These ionization energy values increases from left to right, because if electron come closer to the nucleus, amount of energy required to remove the electron is more. And if the atomic size is very large, then it is the electron is away from the nucleus, so it can be easily removed. So when the atomic size is very large, the atomic ionization enthalpy will be very less. Remember this. So ionization enthalpy increases from left to right, because the nuclear charge effect is there. But I want to explain only one thing with this value. We can see here, scandium is having the first ionization energy 632. See, this increases. In case of vanadium, it is decreases. Chromium, it is 652. Then Ca, the ionization energy values are increases here. This is the first ionization energy. Then second ionization energy values are again very high, because stability is more. Again, the third ionization energy values are very high, because as the stability increases, amount of energy required to remove the electron will be increases. So which question is important for the board exam? It is highlighted here. The ionization enthalpy values of the elements of the third transition series. Third transition series means 3D, 4D, 5D. This is 5D. So we can see with the help of this graph. So the ionization energy values are very high than the ionization energy values of this first transition series. Why this is happening? This is as per the examination. So the answer of this question is, in case of the third transition series, the electron enters in 4f orbital, remember. So in case of this 4f orbital, there is a very poor shielding effect, and due to this very poor shielding effect, the valence electron, they experience the more nuclear attraction. So if the more nuclear attraction is there, the nucleus will pull the electron towards itself, and the amount of energy required to remove the electron will be more. So in case of third transition series, this is a 3D, this is a 4D, and this is a 5D. In case of 5D transition series, ionization energy values are very high than the first transition series. So reason is poor shielding effect of 4f orbitals, and due to this poor shielding effects, the nuclear attraction is more. So the nucleus will pull the electron towards itself, and amount of energy required will be very high. When I'm coming to the metallic character, all these D block elements generally they shows the metallic character, because they having the unpaired electrons. Unpaired electrons are there. They means they will form the covalent bond. These covalent bonds are the metallic bonds. So already this part is discussed. They shows metallic properties. These are very hard, high melting point. They having the close packed structures. Remember, hexagonal close packed structure, then cubic close packed structure, or body centered cubic lattice. In chapter number 1, we will discuss these details. What is meant by close packed structure? No any question will be asked on this metallic character. Remember. Then very important this magnetic properties, because 2 marks question will be 100% there. Calculate the magnetic moment. So make a star there, very important. So 1 mark or 2 mark numerical will be there on this magnetic properties. So these magnetic properties in case of D block elements are due to the unpaired electrons. So then what is meant by this magnetic properties? Which magnetic properties are there? There are 3 magnetic properties: paramagnetic, diamagnetic, and ferromagnetic. Paramagnetic substances means these are attracted by the magnetic field. Diamagnetic substances are repelled by the magnetic field. And ferromagnetic substances means these are very strongly attracted by the magnetic field. These are the 3 different magnetic properties. Paramagnetic attracted, ferromagnetic strongly attracted, and diamagnetics are not attracted because there is no unpaired electrons. In case of paramagnetic, I will explain. See, the examples are compounds containing Cu2 plus. Cu2 plus means it is very clear. Cu2 plus means 2 electrons are given. From 4s 1 electron is given, and from 3d10 1 electron will be given. So it will be 3d9. So Cu2 plus is paramagnetic because unpaired electrons are there. Mn2 plus unpaired electrons are there. P3 plus unpaired electrons are there. So these are the paramagnetic substances. Then when the pairing is there, it is called as a diamagnetic substances. For example, Zn2 plus, no any unpaired electron is there. Cu1 plus, no any unpaired electron is there. Scandium3 plus, no any unpaired electron is there. If there is no any unpaired electron, it becomes diamagnetic, remember. If the unpaired electrons are there, it becomes paramagnetic. And if there is a more number of unpaired electrons are there, then it is ferromagnetic. The substances iron, cobalt, nickel, these are called as ferromagnetic because these are very strongly attracted by the magnet. Then, so permanent magnet can be prepared by using this iron, cobalt and nickel, remember. This can be asked for the CET also, for the NEET exam also, and for the JEE also. So for the permanent magnet, this iron, cobalt and nickels are used because these are ferromagnetic. So each unpaired electron gives the small magnetic moment. Remember, magnetic moment is nothing but due to the spin angular momentum, they generates magnetic moment. So magnetic moment is calculated by using this formula. This formula is called a spin only formula. Mu is equal to under root n into bracket n plus 2. Here n indicates the number of unpaired electrons, and Bm, this is unit of magnetic moment. Bm is the Bohr magneton. So if you know the number of unpaired electrons, you can calculate the magnetic moment. So when a problem is given, calculate the spin only magnetic moment of the divalent cation. Remember, divalent means 2 plus. Divalent cation, this word will be given for the examination. Divalent indicates 2 plus, divalent. Cation, because cation, you know, the positively charged, atomic number is given 25. Immediately, if it is a 25, we have to guess it is 4s2 3d5. So 4s2 3d5, 2 electrons are given from 4s orbital. These 2 electrons will be given, and 3d will contain the 5 unpaired electrons. So the value of n will be 5. So 5 into bracket 5 plus 2, it gives the value 5.92 bm. So tomorrow I will discuss you how to calculate unpaired electrons, because if 2 electrons are given from 4s, there will be unpaired electrons will be 5 unpaired electrons. If you know the unpaired electrons, then it is very easy to calculate the magnetic moment. But if you didn't understand how to calculate the unpaired electrons, then it is very difficult to calculate magnetic moment. One example is given, calculate the magnetic moment by using this spin only formula. This formula is also called as spin only formula, and M2 plus is given. Again, it is divalent, but the number of